So I told some people in office hours today that I would try to make a tutorial that kind of goes up off of the setup process for Vivado, and hopefully this will help you when you're kind of thinking about your lab, how to get up and running with Vivado, and just kind of how the modules and the test benches work, and how to bring your idea, your concept to an actual implementation that'll work on an FPGA. So for this, I don't have my basis board with me, so I'll have to go home and test it. So this might work, it might not, and this is my first time trying to build this. So I'm building it completely from scratch. It might work, it might not. Y'all will work through it with me, so if I run into errors, you'll also run into errors, and we'll kind of fix them together. So I hope it goes well. I hope y'all are able to learn something. Because I haven't done this before before actually recording this video, it might be kind of slow. You might want to watch it at 2x speed. I don't know. But anyway, what I want to do is there are 16 switches on those basis boards. So I want to use half of them to be a 8-bit input, binary input number, and the other half to be an 8-bit input number. And then we're going to use some different modules to either add the two numbers together or subtract them, and then display the output as an 8-bit number on the LED lights. And then I'm going to kind of leave an area where you can extend it and use it on the 7-segment display. So let's get into it. We're going to do this from scratch. So shoot, I just closed Vivado all the way. Alright, so let's create a new project. We'll add the sources later. Let's go ahead and add a constraint file. So just go hit up your basis 3 file. To select your FPGA, it's an Arctic 7. It's got this package, the top option, and then -1, and it's the option in the middle. So this is the part number. Yeah. Okay, so to get this started, we're dealing with 8-bit numbers, so the first thing we need to do is create an 8-bit adder and an 8-bit subtractor. So I'm going to go to this plus, and we're going to create a new file. And let's call this ALU, even though it's not a full arithmetic logic unit. Let's just call it that anyway. And we'll finish that. Let's not worry about ports yet. Alright, go to design sources. Let's open this up. By the way, little life hack, you can do this in VS Code. The IDE is much better, but anyway, I'm doing it in here for right now. I want to change this from ALU to the adder, and we'll also put a subtractor module in here. Module subtractor. Yeah, I think it's OR. If I get that wrong, y'all can make fun of me, that's fine. Alright, so we're going to put an input 31-bit, or 32-bit, oh sorry, it's 8-bit. So 7 down to 0. It's going to be one input. 7 down to 0. B, and then an output is going to be 7 down to 0. We'll just call that C. semicolon, and in module. This is what I'm talking about. So if I shift tab, okay, it actually worked that time. Never mind. Forget I said anything. Okay, so our subtractor, we're just going to do an assign, what's it called? Continuous assignment. So we're going to do assign C equals A minus B. And that's that. And then we need to do the same thing for our adder. Our port list is going to be the same, so I'll just copy that over. Need that. All right. And then this one's going to be assign C equals A plus B. All right. I had to sneeze. Okay. We'll save that. What the heck? My recording software is acting really weird. All right. Yeah, we'll save that. All right, so those are our adders. The next thing I can think of that we're going to need is we're going to need a converter to go from. No, we don't need that. Let's see, what do we need next? Let's build a wrapper. I'm going to call this top. This is going to be our top module for our board. Finish it. Don't worry about the ports. We'll define this later. All right, let's open this up. So, all right, let's talk about inputs. So inputs for our top module, we're going to need the switches. So SW, it's a vector from 15 down to 0. And we're going to have to split those, but we can figure that out in a second. What other inputs do we need? I think that's it. That's all of our inputs. I'd really love to have an input for deciding if we're adding or subtracting, but I have a thought for that, so we'll come back to that. Outputs, for right now, let's output to our LEDs. So we'll say LED, and we're only going to use the bottom 7, so we'll say 7 down to 0. Those will be the only ones we uncomment. And that should be it. All right, now we have to instantiate our lovely adders and subtractors. So we'll say adder A1, and then for our A input, we're going to do SW, and we'll go 15 down to 8. For our B, we'll have SW, we'll go 7 down to 0. And for our output, we'll just do LED. Oh, here's what we could do. Let's use all of our LEDs, and the top however many will be for the subtraction, and the bottom ones will be for addition. So we'll say 7 down to 0 for this, and for subtractor S1, we'll have SW 15 down to 8, SW 7 down to 0, and LED Let's do 15 down to 8. Okay, cool. I think that's about it. Next thing we want to do is add a test bench. This is where we can actually test this. Real quick, you'll see this updates where your adder and subtractor are part of top, and then it's gone ahead and listed top as the top module. But before I actually test it on the board and go through synthesis and implementation and generating the bit stream, which takes forever, I'm going to want to do some simulations just to kind of debug it and make sure everything's working how it should be. So I will create a new design source, and this one will be test bench. Test bench does not have any input or output ports, so yes, that's exactly how we want it. And after it creates it, we'll double click it to open it up. All right. So let's think about what we need to drive. We want our inputs into our modules to be registers, so we can set them and that they have memory. But we want our outputs to be something that can be driven, so they need to be wires. Okay, so hopefully that makes sense. So in this case, we're going to have our input switches basically, and let's say these are registers. So we'll say reg. You know what? We can set these as integers, because integer just implies that it's a 32-bit register. Oh, we're doing 8-bit, aren't we? I wonder if this, I can't remember if this has byte or short. Y'all would know better than me, because it's probably come up in one of the lecture slides. I'm just going to do a wire vector 7 down to 0. We'll call this this A, wire 7 down to 0. Oh, and these are registers, sorry, because these are memory elements. B, and then the wire is the output, and it's going to be 7 down to 0. I'll call this one sum, and then wire 7 down to 0 difference. Not the world's greatest speller. Okay. And then we're going to go ahead and re-implement our adder and subtractor here. So adder A, B, sum, and sorry, I didn't do that right. Adder A1, A, B, sum, and then subtractor S1, A, B, difference. All right, and now we can do an initial block. An initial block just runs one time, so it's kind of it's a good entry level into your test bench. So this is where stuff starts kind of sequentially occurring. So I'm going to start by setting A equal to 8-bit decimal value 12. B equals 8-bit decimal value 7. Then we will wait 4 time steps and set A equal to, let's just change B. B equals 30. Alright, we'll wait another 4 time steps and then let's set A equal to, I'm just making up stuff, 21. And wait another 4 time steps, and you kind of get what's going on. I'm just supplying inputs into the system and be able to see what the outputs are. That's probably pretty good. I'll go ahead and end this initial block, and hopefully nothing will complain. Alright, it all looks pretty good. And we'll save this. So if I run simulation, it'll take it a little bit of time, but it doesn't take long before it figures out what the logic is doing, and you'll be able to test if you have any major errors. Alright, cool. That does not look right. Let's see what we got going on. Oh, I know what's going on. Let's close our simulation back. So this should be set as your top module, but for simulation, we actually want to set our test bench as our top module. Alright, cool. Because we are not driving anything in that other top module. In the test bench, we're actually driving stuff with this. Also, don't forget the initial block and these delays right here are not synthesizable. They only work in simulation. That's important. Alright, so let's go ahead and run our simulation. So see, I made a mistake there, and it's not going to take that long to reset everything. That's why simulation is really nice. It's relatively fast. It doesn't take 3 minutes to synthesize everything and implement it and stuff. Alright, cool. So now we have this, and I forgot something else. Go back to your test bench and end it with stop. And that's just going to make it where it stops and the window is small enough that you can see everything really well. We could have just scaled the window, but this is a better way to do it. Just add stop at the very end. Alright, cool. And now we can see what's going on. I don't know about y'all, but I normally read in signed decimal instead of binary or hexadecimal. So you can use this radix thing right here. Change it to signed decimal. Yeah, it does a much better job of showing what's going on. Alright, so here we can see what A's doing. You can actually do a drop down and see the actual individual bits and how they're changing. But this gives you the decimal equivalent up here. So for 1, 2, 3, 4 time steps, A was 12, B was 7, the sum is 19, and the difference is 5. Then we had B went to 30, the sum is 42, the difference is negative 18, and so on. 20 and 30, 51, and negative 9. Alright, so that part works. You can also save this. You can save this graph. So Control S. You can name it something memorable, and then it will save your base display and other things like that. You can make these pretty complex. You can like add a divider in here. It's like you can have outputs and move this divider between these, and so it'll help you visualize things and see stuff like that. So that might be helpful. All right, so now we kind of have our test bench working. I think most of this works. So now we can start focusing on this top module. So right now it ties it to these LEDs. We could instead tie this to a like intermediate. So we could do, let's say, I think it's wire, buffer, down to 0. The reason we can do this is we can add additional outputs. So 15 into 0. So maybe we want to pass this to a 7-segment display. So we can add that output and also assign that seg disk equals buffer. All right, but let's not do that right now. We can do that later. So right now, I'll just leave it like that. All right, now we have to talk about, since this is the top module, we need these tied to actual nets that are on the development board. And to do that, we have to open up our config file. So I'm going to close my simulation. We'll save that. And open up my constraints file. Alright, I'm going to go back to my top module. And my input are these switches, 15 down to 0. So if I go here, I can see those right here. And I'm just going to select all of them, Control / uncomment them, and make sure this one is SW15. On some of y'all's it'll be reset instead. You can just change it to SW15. But we need those, and then here's all of our LEDs. So same thing, select them all, Control / to uncomment them. Save that. Now, like I said, I don't have my board, so I'm going to try going through everything, doing the synthesis, the implementation, and generating the bitstream, and then when I get home, I'll try to run it on the board. But running it on the board shouldn't cause any big errors, so y'all should be able to figure that part out. I imagine if it fails, it's going to fail in the synthesis or the implementation or even the bitstream generation, and if it does, we'll talk about those errors. So I'm going to pause it while this is going. Okay, cool. Well, our bitstream generated successfully. So your next step would be open the hardware manager. You can also do that down here. We'll click OK. And it's going to open up. Next thing would be open target and then hit auto connect. And if your board's plugged up, it should connect. Mine is not, so it's not going to connect. But it will connect, and then you'll have another button right here that says program device. And you should be able to program the device, and then you'll be able to test it, and hopefully it'll work. So I'm going to go home and test it. I hope this works out for y'all. I hope I was able to explain everything well. If not, just shoot me an email or a Teams message, and I'll try to address whatever that is. Hope this is helpful. Let me know if y'all need any other help, and I'll talk to y'all later.